is the Hilbert space of local Hilbert space times the number of spins we have. And in this case, it's 2 to the n. Okay, so 2 to the n is exponential. The Hilbert space is exponentially large in the number of spins we have. Okay, so how do we do that? If we want to store the state of, say, for example, this system, you need to have at least 2 to the 6, which is 2 to the 6, which is 64 complex numbers coefficient, right? And to give you an idea about what is the problem, consider the fastest or the biggest computer with memory in the world, supercomputer in the world, which is in Japan, and few of them are in the US and China. They have a memory of something like 5 petabytes. Now, 5 petabytes is about 10 to the 3 terabyte. It's about 10 to the 6 GB, and it's about 10 to the 15 bytes, right? Now, if you just assume that you need 1 byte to store one complex number, then you can show that, for example, 10 to the 15 can be written as approximately as this, and 10 to the 3 is basically 2 to the 10. So 10 to the 15 is 2 to the 50 approximately. So that means even on the biggest supercomputer memory-wise we have in the world right now today, we can store the full state of only 50 spins. And maybe after every 2 years, this doubles. So for example, if I come back after 4 years, maybe 51 spins, maybe 52 spins, maybe 53. But this number is not useful for physics purposes, because in physics, we often want to take the thermodynamic limit. Because when we have quantum phase transitions or usual phase transition, you need a very large number of degrees of freedom, or say spins, for example. It has to go to infinity. And 50 is obviously not very large. So what I'm saying is we cannot study, for example, quantum system of more than 50 spins properly on a computer we have right now. So how do we do it right now? And the way we do it right now is by using tensor networks. So tensor network says that you don't need to construct or store all the complex coefficients, but you can be smart and only store some of them which are relevant for the purposes of the physics you want to extract. So that is the approach tensor networks take. That is why it is called classical method of doing quantum many-body, right? Now you can do the same thing using a quantum computer. And for that, for example, you need 50 qubits. So if you have 50 spins, 50 spin half, you need 50 qubits. And that is why people are also exploring that, because tensor networks might be very good in lower dimensions, for example, for one-dimensional quantum systems, maybe for two, but they cannot solve us 3 plus 1 dimensional Hamiltonians. You cannot do real-time scattering using tensor networks in higher dimensions. You can do those things only in smaller dimensions. So even being very innovative about the methods like tensor networks, you cannot scale it. So doing quantum many-body systems in higher dimension is still an open problem. That is why people are exploring methods such as quantum computation, right? So right now I'm working mostly on quantum computation. I also work on tensor networks, but I just wanted to tell you that both of them have the same goal. And that is to do simulations of quantum many-body systems or gauge theories, which have infinite or very large number of degrees of freedom. So for example, what this basically means is for 50 spins, you can have basically a site of 7 by 7, for example, right? And that is the best we can do. You cannot, for example, align 8 by 8 because that's more than the limit. So this is the limit we have right now. Right? Okay. You see the screen, right? Sorry, so it suddenly went off on me. Hello?
Yeah, we can see the screen.
Okay.
And we can see your mouse, yeah.
Okay, good. Okay, so in these lectures, what I'll talk about is the plan is to tell you about the Lagrangian and the Hamiltonian approach two tensor networks, because tensor networks, you can think of both tensor networks, both in terms of Hamiltonian formalism and Lagrangian formalism. So I'll talk about first about the Hamiltonian, which is called the matrix product state. And then initially in the later half of these set of 4 lectures, I'll go to Lagrangian aspect where we do real space renormalization group using tensors. So tensors are very effective in the sense that you can approach them using both Hamiltonian picture and the Lagrangian picture. And they can assist in both the ways of dealing with spin systems or gauge theories, for example, right? So this is one of their advantages. Then, for example, I'll also use some simple systems to show you exact diagonalization. And for these, we will use Google Colab. We'll go online and write some small pieces of code. So we'll do exact diagonalization for quantum Ising model of some n spins. And then I'll talk about how we can get started with tensors, and I'll show you what tensor contractions are, what is SVD, and Schmidt decomposition, hopefully in the notebooks. And then eventually we want to go to real space RG. So I'll show you 2-dimensional classical Ising model solution, which was well-known solution given by Onsager in 44 using real space tensor RG methods. So for example, we can solve 2D classical Ising model in 10-15 seconds on the laptop, which is impossible using any other numerical method. So it's very efficient in the sense that you can, it's much faster than say Monte Carlo or any spin algorithms you might know. So tensor network is the state of the art. That is why we say it's the state of the art. Okay, so this is the basic framework. And then, for example, I'll also talk about a lot of things intermediate. For example, I'll start by talking about entanglement and other things. So we'll see. But the basic idea is that I'll talk about the Lagrangian and the Hamiltonian approaches, some properties about tensors, SVD, Schmidt, and real space. If we go to real space and if we get a lot of, if we have some time, then we'll do some interesting models such as XY model, which has a famous BKT phase transition, topic of Nobel Prize in 2016. It's infinite order topological transition, very unusual in physics sense. So that is the XY model. And then I'll also talk about, if I have time, a SU2 Wilson action using TRG. So this is the plan. So let's start by considering now just spin 1. So for example, I just said that spin 1 has 2 states, 0 and 1. We represent 0 by spin up like this, and we represent 1 as spin down like this, right? Now, one of the things about quantum mechanics is that they can be in a superposition state. So superposition, or in fact, uniform superposition in this sense, says that the state can just be written as like this, right? So if I have a spin half, and which is represented by 1 qubit, it can be in a superposition state, right? Now consider 2 qubits. 2 qubits obviously will have 4 states, and it's all clear to see what those are. So up, 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 down, down, up, down, down. And now in this case, since we have these 4 states, we can also consider what we call as 2 qubits entanglement, 2 qubit entanglement. So for example, this is well known by due to the things we study in quantum mechanics. Say, for example, if I want to construct a Bell state, I can do it like this, right? Now, this Bell state is a pure state, and it's also maximally entangled, right? So these are the two interesting properties we have when we do quantum computing, for example. You can have a qubit, which is in a superposition state, or you can have two qubits or multipartite systems, which are entangled. So for example, in this case, it's a bipartite system because there's a HA corresponding to the first element of this ket and the second vector belonging to HP, and they can be in an entangled state, right? Now, one of the things which we can keep in mind is that usually when you read any textbooks or see the literature, 0 is represented like this, and 1 is represented like this. Because we know that every ket vector can be represented by a column vector, and this 0 is represented by this and 1 by this. So in this case, for example, 0, 0 is nothing but 1, 0, 0, 0, and 1, 1 is nothing but 0, 0, 0, 1. So for example, the Bell state has a representation like this. Now, this is a column vector representation. You can also have a matricize. You can matricize this vector, and the way you matricize is like this. So Bell state can be written like this. It can be matricized, or if you start from the matrix representation, you can vectorize. So these are different representations of this state. Yeah. Right. So is there anything which is any questions at this point?
Okay. What is the map to make it a matrix? I mean, are we just reading them off one by one, or?
Yes. So example, this is like 0, 0, this is 0, 1, this is 1, 0, 1, 1. So if the space is local, Hilbert space is two-dimensional, you go two along direction 2 on along a column vector, along a row vector, and then you change rows basically. So this is just called a matricizing the vector basically. So how you store a one-dimensional object as a two-dimensional object. Okay, so now what we have is, I said that the Bell state is maximally entangled and it's pure. So for example, if I ask you, this is a short thing, is 1 over 2, 0, 0, 0, 1, 1, 0, 1, 1 entangled? So is this state entangled? And the answer is, this state is not entangled. This state is not entangled because, so this will eventually lead us to what we really mean by entanglement in the sense of doing calculations. So if you just write something like this, we can show that this state is equal to this state. And if a state can be represented as a product, for example, if psi can be represented as some psi A times psi B, then it's a product state and it's not entangled. So this state is not entangled. You can show that this Bell state, which we wrote here, cannot be written as a product state. So that is why it's entangled. And the reason of maximally entangled is because of something where, for example, you can construct the density matrix. Maybe I'll do that now. We'll see why I said that it's maximally entangled. So the basic idea is if there are more terms in the state, for example, there are 4 terms here, for example, 0, 0, 0, 1, but there are only 2, and this is not entangled, and this is entangled. So tensor networks, the methods we are going to talk about, for example, MPS methods are only good when the system is slightly entangled. I'll come to the definition of what I mean by slightly entangled. So now we know what is maximally entangled means and what is no entangled means, and then we'll come to the definition of slightly entangled, which lies somewhere in between those two extremes. Okay. For example, one of the things we can check for the Bell state is, I said that the Bell state is pure. So the definition of pure state is that, for example, if you construct a density matrix rho, and you construct a row square, trace of row is always selected, taken to be 1. So it's always normalized such that the trace is equal to 1. If the trace of row square is also equal to 1, then the state is pure. If trace of row square is less than 1, then the state is called mixed. And it is easy exercise to show that for Bell state, trace of row equals trace of row square equals to 1. So it's a pure state. Bell state is a pure state. So I won't do this proof, but it's easy to show. You have the psi. So the definition of row is you take the outer product. So if you have a vector, you want to make a matrix, you take the outer product of these two, and then you compute the trace and things like that. So it's easy to check that it's a pure state. So it's pure state and also maximally entangled state. Okay, so now let's just, I don't have, okay, so maybe. This is about 2-qubit system. Now we can say, okay, what about 3-qubit system? So, okay, let me just mention the multipartite entanglement is a current area of research, and there are a lot of interesting work happening. So we cannot go to like a general state, but for example, 3-qubit entangled state, let me just mention, because this is also useful for quantum computing and for tensor networks, because for example, one of these states can be exactly represented by a tensor network. So what are 3-qubit entangled state? There are two classes. The first one is called the GHZ state. So GHZ state is just a generalization of the Bell state to 3 qubits, and it's given by. So this is the GHZ state. Then there is another state of 3 qubits, which is entangled, called the W state. And in this case, it's 0, 0, 1, 0, 1, 0, 1, 0, 0. And if you have 3 qubits and you want to entangle them and you create an entangled state, then whatever state you create, that whatever entangled state you create can be transformed to one of these by some local operations and other things, which we will not go into, but they can be converted into these two wide, broad classes. So for example, all 3-qubit entangled state either belong to the GSZ class or the W state class. They are not the same because GSZ is maximally entangled. W state is not maximally entangled, but it is entangled. And they have other properties when you trace out one of the subsystems. So for example, one of the important things we learned with density matrix is that density matrix can be, for example, in this case, it can be over 3 qubits, but then you can trace out 1 qubit or 2 qubits and just left with the density matrix on the subsystem of that entire system. And under those things, these two states have different properties. And that is why these are two classes of 3-qubit entangled state, right? So you can keep going and then consider what is n qubit. So n qubit entanglement is active area of research, and there is a lot of nice results related to n qubit entanglement. For example, there's something called absolutely maximally entangled. So you can create n qubit entangled state, and then you can trace out some systems and see their properties. So it's a wide area of research. So the basic idea about this is that the quantum states, quantum any body which we want to study can be entangled in different ways. And tensor network has to only, tensor networks can only be sufficient under some situations or some conditions. And we'll come to those later in the lecture. So this is all I wanted to say about the quantum computing where with entanglement and things like that. Now, one of the important things which we use in tensor networks is what we call the Schmidt decomposition theorem. So for example, if I have a state psi, a pure state of system AB, right, where, for example, A and B can be both spin half systems with local Hilbert space of dimension 2, then this theorem says that if you have psi AB, it is always possible to write this psi as sum over some lambda I this is the Schmidt decomposition theorem. So I goes from 1 to say n, where n is the minimum of HA comma HB, where HA is the Hilbert space of belonging to the system to the part A, and HB is the Hilbert space of B. So if both of them are spin half systems, this is 2, 2, and n is also 2, right? So this is a very important theorem in tensor networks, at least MPS methods. And this was, I think, the founding ground of over which most of these constructions are based. So this is a simple example for a bipartite system, which psi is AB, but this can be extended to, for example, multipartite things and so on. It becomes more complicated, obviously, but the basic idea is that if you have a bipartite system, there's a psi, then you can always go to a basis which is called the Schmidt basis. This basis is called Schmidt basis. And these coefficients are called the Schmidt coefficients. You can always go to a basis, Schmidt basis, and in that case, the psi can be written like this, right? So this is one of the things which we'll use. So how is this useful? Let's see a small example of how this is coming into play. So for example, I can write some psi as, say, for example, two spins, both of them are 0 or 1, can be 0 or 1 spin half system. And then you can write something like CSS, the coefficients of S prime. So when I write something like this, I also sometimes will write like this. So for example, when I was initially writing 0, 1, I was just using this notation. So this is what it is. And I can write it like this, right? A general state. Now, the thing is, this is a matrix, which is basically saying what is the sort of overlap between these two things. So if this is a matrix, I can do some operation on this, which we'll come back to later, what I mean. Just a second. So B is comma A. So I'm writing a matrix like this, and this result is a standard linear algebra result, which is called the singular value decomposition. So before, so we'll come to singular value decomposition in more detail later on, but maybe for now, I can just say that if I have a matrix, for example, a matrix can be drawn with two legs. So for example, if I draw a matrix like this, I'll come to this notation later on. This is known as the tensor notation. So for now, just think about this as some block with two legs. Two legs means that it is a matrix. If you have a matrix, doesn't matter whether it's a square matrix or a rectangular matrix. Any matrix, that's why we have two legs, any matrix can be decomposed into a set of three matrices, U, S, V, and this is known as singular value decomposition, where S are the singular values. For example, this can be a diagonal matrix, right? And you can rewrite this thing as this one leg, one leg, one leg going here, one leg going here, one leg going here. Just a second. Yes. So this leg is not there, right? So we have two legs at the start, we have two legs at the end, but the way we decompose this is different, and that is what is known as SVD. So this is a matrix, first leg, second leg. This is also a matrix, this is also a matrix. So this is what I'm using here. This is known as the singular value decomposition. And there's a relation between Schmidt decomposition and singular value. And that is why when we do tensor networks, a lot of times we do singular value decomposition. Because singular value decomposition, as was shown by Young, Eckert, and Mirsky in 1936, 36. It is one of the best ways of approximating a bigger rank matrix with a smaller line. And this has huge applications in machine learning, quantum computation, quantum information, and things like that. Whenever you see anything on inline, for example, say an image which is compressed, we always use SVD. That is the basic foundation of all the images you see online, all the machine learning. Everyone does SVD because you don't want to deal with the bigger matrix, obviously, because we know we saw at the starting that it cannot be fit into the memory. So we start with, say, for example, we say, oh, the state of 52 spins can be represented by a huge matrix, but I don't want to deal with that matrix. So how do I go to the smaller approximation? And the way you go there is using the SVD, right? So if you do SVD correctly, then you can still have the same information about the bigger matrix, but at a much less reduced cost, for example. And that is advantageous, and that is why it's used everywhere. So this was the basic digression into this SVD thing.
Sorry, Raghav?
Yes.
I'm not sure I see, where is the approximation here?
Okay.
Or
Yes.
are you going to say that?
Yeah. That's a good point. So let's see. Yeah, I was missing that point. Thank you for. Okay, so where is the approximation here? The approximation is in the fact that if, say, for example, the A's are only running from 1 to chi, whereas the dimension of this matrices can be up to n. So this is an n by n matrix. And these A's, for example, the singular values, only run from 1 to chi. And for example, let me just delete this for the time being. Okay, so if I have a matrix, which is, say, SCS S prime, which is of n by n, then I approximate this by SA lambda AA V S prime A, where A is running from 1 to chi, where chi is much less than n. And that is the approximation, in the sense that you decompose the matrix, but then you say, oh, I don't want to keep the very small singular values. For example, I don't want to keep so this matrix is completely like this, but you want to say that, oh, I don't want to keep the lower part. And it turns out that this part you ignore can be huge. For example, this can be 60%, 70% of the entire
matrix. You seem to have broken up a little bit. Maybe you can repeat the last 10 seconds.
Okay, so the way the approximation is coming into is that when I start with a matrix, which is n by n, if I keep all the n eigenvalues, so for example, if A goes from 1 to n, then there is no approximation. But now I want to construct SVD of a matrix which is huge, say billion times billion. And then A cannot go from 1 to n. So A goes from 1 to some chi. And that chi is much smaller than n. And that is why this is an approximation. But it's a good approximation because even after leaving the small eigenvalues, the physics I get, or the interesting things which I construct from this matrix, is the same as this. And that is related to this paper by Young and Eckert from 36, where they say that if the matrices are closed within two norms, some given two norm, which is called the Frobenius norm, then it makes a good approximation. Okay.
So you first organize the eigenvalues from larger to smaller in magnitude.
Yes.
And you keep the larger ones up to the accuracy that you want to,
yes.
the approximation that you want.
Yes. So you keep the largest chi eigenvalues. Yeah, I think, yeah. Thanks for the clarification. Yeah, I should have been more clear about that. So I hope this is now clear. We'll come
Sorry,
back.
to know the eigenvalues, you have to diagonalize the matrix first, or can you? Is that okay? Or
You
don't you need computational power to diagonalize your matrix first to know the eigenvalues, or can you just approximate the larger ones without the computation of the full thing?
So there are different ways of doing that, but you're right that SVD is costly. It's not a efficient approximation in the sense that it's not efficient computationally. It has cost which grows at least as the cube of the matrix, which is the cost of the matrix multiplication, or for example, inverse and things like that. So it's not cheap. That is what I'm saying, and that is why SVD is sometimes the bottleneck, because even if you're doing SVD, you still have to diagonalize or deal with big matrices which have complexity going like cubic in the size. But there's no smaller computationally tractable problem which can give you the same approximation as SVD. So there's something called a randomized SVD, where you actually don't do, and it's little more efficient than the normal SVD, is the standard SVD, but they can be unstable numerically sometimes. So it's like a hit and miss. Sometimes that might work, sometimes it might not work. So that is the problem. But yes, SVD is an expensive operation, and even in the real space tensor renormalization group methods we do, SVD is the bottleneck sometimes. So we have to use different ways of speeding that up.
Okay, thank you.
So let's see. Yeah, we're going back to this thing now. I can just, yeah, we'll come back to this later on in the coding session also. So you can rewrite this as this, and then, for example, it's straightforward to show that you can rewrite this in the form which we showed before, where this is some lambda I, this is ui, this is vi, and this is I going from 1 to chi, for example. For a general system, this I here. So this is not anymore, for example, a bipartite system, but it can have n spins. So it can have n spins, but the local Hilbert space is still two-dimensional, and you can go from 1 to chi. Now the chi which we saw here, which is the number of Schmidt values or the Schmidt coefficients you take in the decomposition, is known as the bond dimension of the tensor, or bond dimension of the tensor networks or the tensor representations we use. So for example, you might read some paper and see that they refer to chi as bond dimension in MPS, and that is exactly what this is. So it basically tells you how many singular values or the Schmidt coefficients you're keeping. Now the thing is, if there is just one Schmidt coefficient, that means the state psi can be written as something like special U, special B. And this is a product state. So for example, if the number of Schmidt coefficients is 1, the state is a product state. If the number of Schmidt coefficients is greater than 1, it's an entangled state. But if chi is still less than much less than, I would rather say, then the total Hilbert space dimensions, then the system is called slightly entangled. So how many chi's what value of chi you have, for example, tells you how about the entangled nature of the initial state, for example, psi state. If you have to keep more chi's to minimize or keep some norm under some precision, then it's an entangled state. If you just have to keep one, then it's a product state. Matrix product representations are for a slightly entangled system, and that means chi is neither very small nor very large. It's somewhere in between. The system is slightly entangled, but it is not spanning the complete. It's not equal to the dimension of the Hilbert space, linear dimension of the Hilbert space or something, right? And that is exactly where the tensor network methods are effective. That you can have this chi reasonably small, but still extract meaningful physics out of it, right? And this chi, we call this chi as the bond dimension. Okay, so once we have that, then the next thing we want to say is that, for example, if if the sum of all lambdas or the Schmidt coefficients, sorry, the sum of all lambda is equal to 1 because it's normalized to 1. And then if all the lambdas are the same, that is all lambda I is equal to 1 over chi, then what we can show is that the entropy, which is given by, say, is equal to log chi, right? So if all the Schmidt coefficients have the same weight, basically, right? And you take out, you compute the von Neumann entropy of those Schmidt coefficients, for example, you'll see that it can have a maximal entropy defined like this as log chi. So this also limits the amount of entanglement an MPS can have. So it's always upper bounded by the log of the bond dimension. So if you take a bigger bond dimension, it can describe a system which has a slightly more entropy, has more entropy. Right. So, for example, we'll come back to later about the scaling of these entropies in different dimensions, and we'll see what volume law and area laws and those things, and then we'll come back to this. But the point for now is that this can be if there's a tensor network with this chi or a MPS description or a tensor network description with some where we are doing Schmidt coefficients, then the maximal coefficients is maximal entropy is log chi. Right? Okay, so now we come back to the old description that how do we represent a state psi by matrix product state. And we'll also now see why it is called matrix product state. So for example, I want to represent this psi. And the way I represent this psi is by introducing some tensor, a 3 object tensor, which we call A. So for example, let's say that there is an A on site N, and it acts on a vector like this. And if I do the sum from 1 to N, then it gives an approximation of psi. How to see this diagrammatically? The way to see this diagrammatically is something like this. So psi can be something like so this goes from 1 to N. And the Hilbert space to the N dimension. The matrix product approximation is rewriting this psi as where these go from 1 to N, and this tensor is called as tensor A. And these indices you see at the top are the physical indices. So they go from 0, 1. So basically, they are SI, S, and SIs go from 0, or 0 or 1. Right? So if I am representing an object like this is the state of the, say, for example, N spins and has 2 to the N Hilbert space. The matrix product representation represents this state by some other network, which is called a tensor network, because these are tensor. You can see that the object A is a rank 3 tensor, and it's a rank 3 tensor because it has a leg on the left, leg on the top, leg on the right. The leg on the right is the physical index. And the physical index is the index which actually is part of the initial system. So for example, the physical index in this case is 0 or 1. The good thing about this is to write a state like this, you need 2 to the n coefficient, but to write a state like this, how many coefficients do you need? You just need order, number of spins, which is n, the dimensionality of the Hilbert space, local Hilbert space D, and then each of these bonds are chi. It's the same chi we saw before. So the number of complex coefficients which is describing this matrix product state is order n d chi square. Now d is 2, so we can put 2. So it's 2 chi square times n. And what was the initial cost? The initial cost was 2 to the n. So what is the difference between, what is the magic? This is a magic happening here because initially it was exponential in the number of spins, and now it's linear in the number of spins. So if I could do 50 spins here, I can do 1,000, 2,000 spins here. And that is why tensor network is the state-of-the-art method of doing quantum many-body systems these days, because it tells you that you can go from exponential in n to a linear in n. And that's like exponential advantage right here. So the number of coefficients we need depends on chi, obviously. If you find that you're describing a system which is closer to criticality or has a bigger correlation length, then you will see that chi needs to be bigger. If you are describing a system which is very nice, gapped, is very away from any critical point, then chi can be small and you can still draw meaningful physics out of it. So how big chi is the problem. Like, it is the important question in matrix product state representation. So for example, but if chi is finite for a gapped system, then you can have this parameter and it's an exponential quantity. Yes.
Is chi going up to n as before, or chi not can be larger than n? Or
no, yeah. So chi is obviously much smaller than chi. So chi can be anything which is at least not exponential in n, for example. It can be any number which is not exponential. So I cannot say that chi is like 2 to the n. That's not what you do. So it's like it has to be sufficiently large that is still you have some advantage over this. If you take chi such that you have the same complexity, then there is no point of doing MPS states.
okay, thanks.
Yes. So chi can be, usually what we do is that in practical calculations, we take chi bigger and bigger and then see the convergence in the properties. So for example, the convergence in the scaling dimension of some CFT, if we are using tensor networks to describe a CFT, or convergence in the free energy. So if the free energy is not changing, is accurate up to some 10 to the minus 10, when you take chi from 100 to 200, you don't care that much. But if the free energy and things are changing, then you keep on increasing chi unless you see a saturation in chi. Okay.
Here you represented your psi. It looks a bit like a spin chain or like a one-dimensional.
Yes.
But should I also think we can do the same for higher dimensional? So that is, or that's coming, I guess.
No, so the thing is that it works the best in one-dimensional spin chain. If you take a two-dimensional spin chain, then these optimization and the SVD is not very effective in the sense that the approximation does not hold that well. I'll come to the reason of that. It's related to the area law of entanglement entropy and things like that in lower dimensions. For example, in so area law for the entropy for gap system goes like area law, but for area law in 1D, it's like a constant, right? A to the length LD minus 1 is D is 1, so L equals 0, doesn't depend on L at all. But in higher dimension, it does. And when it does, then these approximations are not that solid. So that is why the two-dimensional spin models, so for example, tensor networks doesn't work that well for 2D quantum spin chains or higher dimensions. And that is still people are exploring that direction.
Okay, thanks.
Is there a periodicity condition also apply here? Because this first thought is known that
yeah, so the question, if it wasn't heard, is there a periodicity condition that applies here?
Oh, yeah. So
because
Yeah, so let me just, before saying that, let me just fix this, that there's no leg here. So this can be, matrix product state can be done for both periodic and open boundary condition. If it is periodic, then you have to connect both ends. But if it's open, you can just leave it like that. So for example, this is open, and the periodic will have one leg here, and then you have to contract them. So you can have different boundary conditions. Is that clear?
Yes, yes.
Okay.
Any other questions, maybe? Okay, no, I think you can go ahead.
Okay. So now, since we saw that, for example, let's see, yeah, one of the things which I wanted to say in the last 8-9 minutes we have is that we talked about this state initially. For example, I said that a state psi, which was written as this, can be written as a product state, and that is why this state is not entangled. So we already saw this before. So let's look at the representation of the state, for example. And we use the matrix representation, which I also described. So the matrix representation of this state is yeah. So we can consider some other example. Let's see. So 0, 0, 1, 0. Yeah, let's put a negative sign because that is what I have. Let's see. Let's put a negative sign for this. Yeah. This state is also not entangled. It can be checked. It's a superposition of plus state and a minus state. So for example, so what is the plus state? Plus state is in minus state is sorry. So this can be, it is also not entangled. If you write a matrix representation of this, you can write something like this. And if you do a SVD of this state and you find U, the singular values, and V, you will see that the singular values for this case, or the singular value matrix, is just equal to this. You can do this exercise, or we can do this in the computation. It's very straightforward. You just define this matrix in Python, you do a SVD. We'll show you, we'll discuss how to do SVD of a matrix in the notebooks later on. And then it can be shown that the singular value is this. And as it should be, it has just one singular value. And that is why it is not entangled, right? If you have just one singular value, it's a product state. If you have more than one, it's slightly entangled. If it is very large, equal to the Hilbert space, then it's very entangled, right? So this was the small example. And this SVD is what we'll do in the notebooks. Maybe we'll also consider this example. Yes. So is there any question at this point?
This example.
A question is, what is the chi in this example? Is chi is equal to 1? Or...
Chi is equal to 1, yes. Because you just need one singular value, basically. So chi is 1. Chi is always how many singular values we keep in the S matrix. In this, we just need to keep 1 because there's just one non-zero. Okay. Okay, one of the things which I just want to say in the last 5 minutes, and then we'll start from this point for after the coffee break, is that at the moment, whenever, for example, big companies like IBM and there are a lot of quantum computing companies, they want to do something on a quantum computer. And they say, oh, that we have a quantum advantage, or we have a calculation which no classical computer can ever do in meaningful amount of time. The state of the art is always tensor network. We will always see that the tensor network calculation comes and beats the quantum computing algorithm. And this has happened at least 2 or 3 times in the last 3-4 years. So there was a result from IBM last year, which made the press, that they simulated some version of the Ising model on a 127 qubit quantum computer. But then soon, in like 2 weeks, someone came and did an MPS calculation of that. So right now, it's safe to say that the tensor network, or MPS, is better than the quantum computers at the moment. That there is no calculation which you can do on a quantum computer which I cannot reproduce using matrix product state. And that tells you that this is really a very powerful classical algorithm. It is a classical algorithm because this has been done not on few qubits, maybe 100 of qubits. It's entangled, slightly entangled, but it has been reproduced using tensor networks. But this will change, because as quantum computing will explore more entangled systems, you'll need bigger and bigger Chi's to simulate the same using tensor networks, and eventually it will run out of steam. For example, quantum computing can go in the higher dimension. For example, look at 2-dimensional spin systems, then it might be able to beat tensor networks. But it is also not easy or practical at the moment to simulate a 2-dimensional spin chain using quantum computer. So that is why I say at the moment that tensor networks is a better method for physics than quantum computing, because we can do a lot more using tensor networks. But the whole program of quantum computing is to change this narrative and to make quantum computing more powerful than the tensor networks. And that is what we are working on. Like, people all across the world are working on. So for example, right now, it seems like the tensor networks can simulate up to a order of 1,000 spins, which are slightly entangled, in the sense that you can get the same physics. So for example, you can have a spin chain which has n equal to 1,000. You can still do some little time evolution and things like that. And we are doing something like that, but it cannot be done using quantum computers. So it's very powerful at the moment.
Is there a time factor here? Like, is quantum computing faster or tensor network faster for the same number of spins?
So there's a question: is perhaps the quantum computing for the same number of spins? Which one is faster?
Even at the moment, if you talk about which one is faster, I would say the tensor networks are faster than, because the gate operation time using quantum computers are not of the. So for example, in computers, we have like frequency, and the time scales are of gate operation times, for example, are of the order of like 10 to the minus 9 or something. The gate operation time for quantum computing right now is still of the order of. So basically, you have to apply gates, right? When you want to do something, in this case, you have to apply these SVDs. In quantum computing, you have to apply the unitary gates, for example. And every gate has a operation time, which is about 10 to the minus 3, 10 to the minus 6 seconds or something. I'm not sure. Maybe 10 to the minus 5 round. So for example, this is the gate operation time. Now, to simulate maybe 100 spins, you might need to have a quantum circuit with 500 gates or 1,000 gates or 2,000 gates, right? Then you multiply each of these with 1,000, and the time you get is maybe what? If you have 10 to the 3 gates, you can have a time scale of 10 to the minus 2 seconds. And then you have a readout time, for example. You have to read out the classical data from a quantum computer. So you add to that the readout time. So all in all, it might become order 1 second or something like that. That can be done, I think, much faster on a tensor network on a big supercomputer, I think. So I would say that tensor networks running on a supercomputer in Japan or USA is still much faster than any other quantum computing running on IBM hardware by several orders of magnitude, I would say. Yeah, but it's very difficult to compare them exactly, because you have to go at the level of gate operation times and things like that. So there's no well-defined answer to that question, I think. Yeah, but you can compare the QPU time, or the quantum processing unit time, and the CPU time. And I would say that CPU time will still be less than the QPU time. Yeah, so after the coffee break, we'll start by talking about what systems the MPS can describe, because there are some one-dimensional system which is still hard for tensor networks or MPS, and those are the critical systems, for example. And we'll talk about why that is the case. And then the discussion about the critical systems will bring us to the idea of the entanglement entropy scaling. And then that can also be connected to one of the other topics in the in this summer school, which is related to the holographic entanglement entropy. So tensor networks have also some relation to the idea of holographic entanglement entropy and other things. So we'll touch a bit upon that, and then we'll also start using some collab for some simple exercises. Yeah. So are there any questions?
Maybe you want to come closer, or
That's fine. So I just have, Raghav, can you hear me?
Yes, I can hear you. Yeah.
Okay, so I have a couple of questions regarding chi. So in the previous example that we considered about the minus state, you mentioned that chi is equal to 1.
Yeah.
The chi is 1. So it seems that chi is predetermined for us if we choose this state. I thought we had the choice of chi, like we could choose chi as large as we wanted, or as large as our computation
Yes.
power.
Okay, so I understand what you're trying to ask. So let me explain this. So if I have a state which is not entangled or separable, then you don't need a chi greater than 1, because there's just one non-zero Schmidt coefficient. What I meant when I said that you choose chi as big as possible was under the assumption that the system or the multipartite quantum system is slightly entangled. If the system is slightly entangled, then you have a chi. If it is a product state, then forget about chi. We don't even need chi. Just
right. Thank you.
And when I really mean entangled system, then you want to have chi as large as possible, but not exponential in the number of spins.
Yeah.
That is what I mean. I was talking about the general case. This is one extreme where we don't even need to worry about what chi is just 1. Is that clear?
Yeah. Thank you.
Okay.
Any other question? Okay, I think there's no more questions right now. So let's thank Raghav.